understand how to, because there's one index here, this is also now fixed, there's another index here I, right? So I cannot use either I or j as one of the summation index anymore. Those who have taken the transport course might recall the rules about use of summation index. Because after all, what is Zj? Zj is Nj by N. Right? Since I am now going to differentiate with respect to Ni, I have already chosen J as a particular index. When I write N, I cannot choose either I or J as summation, otherwise you will bound to go wrong. So I write this as sum over K equal to 1 to C Nj. So now I ask the question, what is dZj by dNi? Again, I'll apply the quotient rule. This is 2 because Ni appears, well, you can say here, but there is a problem. So now what we will do is I will also restrict I to 1 to C minus 1, and we'll see why that is the case. Because what we see here is that while the Z's run only from 1 to C minus 1, the N runs from 1 to C. Because when I expand it, I get all the C whole numbers, they are all independent variables. Only the whole fractions, only C minus 1 are independent. So when I'm going to start this differentiation with respect to each Ni, right? Now you have to recognize that when we come to NC, there will be probably a difference. So to avoid that, I will now let's just consider I can be anything from 1 to C minus 1 only. So I'll handle those first. Right? And so dZj by dNi is 1 over n square. Quotient rule I am applying. Right? So n square. And then I'll get n times dNj by dNi. So let me write that. Minus Nj times dN by dNi, which is 1. So what is, how do we write dNj by dNi? What is dNj by dNi? How do I represent that? If j is equal to I, it is 1. If j is not equal to I, then it is 0. So we use what is called the Kronecker delta to represent that. It's important to remember that we don't require, because if I is equal to C, that term will not appear actually. So we just focus on that. We encounter what to do with I equal to C later. So this is clearly correct because J runs from 1 to C minus 1. Now I have restricted the I also from 1 to C minus 1. So I don't have to deal with the case of when I have to differentiate with NC. So in any case, this would be N delta Ij minus Nj by N squared. So let's just focus on I equal to 1 to C minus 1. We look at I equal to C. What is the complication? If you are not able to see why I am restricting from I equal to 1 to C minus 1, we'll see that shortly. Right? So I have got this. So this can be written as, I can divide by N. I can write this more compactly as delta Ij by N, right, minus Nj by N. One of the N's can be taken and I can write this as Zj by N. More compactly. So let's now recollect all of these and put this in here. So I'm going to write only first mu equal to mu I from I equal to 1 to C minus 1 alone, and I handle the C case separately. So I am now gathering everything. So it will be E plus N times, right, T minus S over N square minus P minus B over N square, right? Now you already see the Gibbs free energy will emerge out of that, but there will be more to the chemical potential. And then I have this plus sum over J equal to 1 to C minus 1 mu J star and D Z J by D N I, right? Certainly will have this form minus Zj by n. So the point is that n, one of the n's can be cancelled, and this n will cancel with that. So let's now rewrite that. So this will be E minus T over capital S over n, right? That will be minus Ts. I'm now reverting back to the intensive and specific variable, because chemical potential is also like an intensive variable only, right? So I want to go back to, even though it is defined in terms of the extensive variables, if you see even in the pure component, finally I get an expression in terms of the specific variables alone. That itself shows that it's also like a specific property of an intensive variable. So it can be related to that, and the number of moles doesn't come into picture in that property. Same thing we will see here in the C minus Ps plus Pb. Although we haven't introduced A, H and G for the pure components, for the mixture, you can very easily guess they are going to have the same form. In fact, I can define them right now. Since we have introduced it here, I can define A to be E minus Ps, H to be E plus Pb, and G will turn out to be E plus Pb. Because there is the same form, because in defining A, H and G, I am dealing only with this part, which is identical to the pure component. I am not touching this. Because the way we came upon A for the pure component was to eliminate S, and what do we replace it by? Right? We replace it by T, is the independent variable. The dependent variable will turn out to be A. So the same Legendre transform procedure will lead to a similar relation for the mixture. Same thing, I start with SV. Now there are so many other variables, but I don't worry about them in defining A, H and G, because I am dealing with only these two variables. I eliminate one of them at a time, and then I eliminate both of them, and then I get G. However, what is there for there are more numbers of variables to be eliminated and new variables to be defined. So there will be another set of Legendre transforms corresponding to the C minus 1 mole fractions, which I am not going to discuss. They are hardly ever mentioned in any of the standard books. But there is more number of variables to be eliminated, more number of variables corresponding to be replaced, and new functions defined like A, H and G. We are not going to do that right now. Let's get back to this, and what we have is plus sum over J equal to 1 to C Uj star delta Ij minus sum over J equal to 1 to C minus 1 Zj Uj star. This is what we have. You can see it's a lot more complicated than the simple relation. So for the pure component, there is only one chemical potential. It stops at E plus Pv minus Ts, which is equal to G. For the mixture also, it has these terms, but on top of it we have some other terms coming in. Right? So let us now write those terms. So J equal to 1 to C Uj star C minus 1 star. have to be very careful. When you sum, sometimes we sum over all C components, sometimes we sum only over C minus 1. So you have to be very careful to put what your sum you are referring to. Right? So here I have j equal to 1 to C minus 1. What is this now? This sum delta ij mu j star, because I know that this is now a sum over j. I is chosen. So for chosen I run j equal to 1 to C minus 1. What is the term that will contribute to the sum? There is only one term. That is for j equal to I. When j equal to I, that term will have mu I star. So I can replace this like this. So we get this extra term which we cannot avoid. This is what we get relating the chemical potential to the specific quantities. The specific quantities are now not only S, P, E, E and so on, but also the mole fractions and the generalized chemical potential. This seems like a very remote and not familiar relation, right? Which it is actually, it's not very familiar, but we'll try to bring it closer to what we are familiar with. Right? So this is what I have. Right? And then now I stop here for I equal to 1 to C minus 1. What will happen for I equal to C and why I have to distinguish the two? We will now see. So this is mu I for I equal to 1 to C minus 1. Now let's look at what will happen when I equal to C in this. Right? So I have Zj, Dnj. So for n equal to C, right? But j remains from 1 to C minus 1 only. That's important. Zj. So the mole fractions are only C minus 1 in number. Right? And so when I differentiate with that with respect to Nc, what is the difference now between dnj by dni for I equal to 1 to C minus 1, right? And now what is dnc by dnj by dnc? But j runs from only 1 to C minus 1. 0, right? Because that is why we have to distinguish the two. Because this term will not contribute at all, because the Nj and Nc are independent variables. Whereas there, when I consider I from 1 to C minus 1, if j is equal to I, now j cannot be equal to C. That is the point, because we are restricting j to only 1 to C minus 1. J cannot be equal to C. So when I differentiate dnj with respect to dnc, whatever may be j runs from 1 to C minus 1. I also runs from 1 to C minus 1, if I consider that. dnj by dni, if j is equal to I, which it can be, right, then you will get 1. If j is not equal to I, you will get 0. So that's why I had the delta ij. But now, j equal to 1 to C minus 1, now I consider I equal to C. Right? So dnj by dc, since nj is restricted to lie between 1 to C minus 1, for zj lying between 1 to C minus 1. Right? When I differentiate with respect to nc, I will get 0. So dzj by dnc is simply only one term minus nj by n square, which is minus zj by n. So basically, I am not going to get this term at all. So mu c can be easily shown to be E minus Ps plus Pv. Right? So I get only this term minus sum over j equal to 1 to C minus 1. So for that component for which the mole fraction is not included explicitly, because I have a choice. If I have C components, I can pick any C minus 1. So I pick a certain set and call it 1 to C minus 1. So I have left out one mole fraction. So you will find for that, the chemical potential of that component will have a slightly different form. It has to be handled separately. But a striking, we've run out of time, a striking result which we will get is when we do mu I minus mu c, and you can check what you will get, I equal to 1 to c minus 1. What is it that we get? You can easily check. All the terms we cancel and we simply get mu I star or mu j star, whatever. We'll see that in tomorrow's class. You can easily work out the relation.